this case, the excess of negative charges at the top point of the conductor creates its own electric field. Then we get a system two electric fields, the electric field of the Earth E1 and the electric field of excess charges at the top point of the conductor E2. The vectors of the strength of the Earth's electric field E1 near the conductor are everywhere the same in magnitude and direction. The vectors of the electric field strength of the conductor at different points of the field have different magnitudes and directions. According to the principle of superposition of electric fields, the strength of the resulting electric field is equal to the geometric sum of the strength of each of these fields. About the top point of the conductor, the strength vector of these two fields are directed in the same direction, down. Here they add up and give the full strength of the electric field. If we add these vectors geometrically and draw equipotential lines at each point of the field, we get the total electric field in the cross-section of the vertical plane passing through the conductor. It is this electric field that tends to pull out conduction electrons from the top point of the conductor. But electrons don't have enough energy to leave the conductor. This energy is called the work function of the electron from the conductor, and for most metals it is less than 5 electron volts. But an electron in a metal cannot acquire such energy between collision with the crystal lattice of the metal and therefore remains on the surface of the conductor. If we help these excess charges at the top of the conductor to leave this conductor, then the negative charge at the top of the conductor will decrease. The external electric field inside the conductor will no longer be compensated and will again begin to move the conduction electrons up to the upper end of the conductor. Current will flow through it. With the constant removal of excess charges from the top point of the conductor, current will constantly flow in it. In this case, it is enough for us to cut the conductor in any convenient place and turn on the load there, the energy consumer. Then the question remains how to remove excess charges from the top point of the conductor. To do this, you need a device that would help the conduction electrons leave the conductor, the electron emitter or emitter. The emitter can be based on a low-power, high-voltage generator capable of creating a corona discharge around the emitting electrode at the top of the conductor. These high-voltage generators use the industry in smoke detectors, air ionizers, electrostatic paging plants, and various household appliances. The generator creates a spark corona or brush discharge around the conduction electron emitter. Such a discharge is a conductive plasma channel through which conduction electrons freely flow into the atmosphere under the influence of the Earth's electric field. Let us estimate the capacity of such an installation. Let the top point of the conductor be a height of 100 meters. The average electric field strength over the height of the conductor, 100 volts per meter. Then the potential difference of the electric field between the Earth and the upper point of the conductor will be numerically equal to. As a result of our actions, we connected the energy consumer to the global generator of electrical energy. We connected to the negative pole, the Earth, using an ordinary metal conductor, ground, and to the positive pole, the ionosphere, using a very specific conductor, convective current. Convective currents are electric currents caused by the order transport of charged particles. They are common in nature. The most powerful of these are hurricanes and updrafts in the intertropical convergence zone, which carry a huge amount of negative charge into the upper troposphere. I wish everyone a positive charge.